If the universe is so big, so old, so full of stars, where is everyone? It's a simple question. It feels almost childlike, and yet the more we learn about space, the stranger that question becomes. On a clear night, when you look up at the sky, you might see a few thousand stars. It doesn't feel overwhelming. It feels quiet, peaceful. But what you're seeing is only a tiny piece of what's really there. Our galaxy alone, the Milky Way, holds around 100 billion stars. That number is so large it's hard to picture. Imagine every grain of sand on a long beach stretching for miles. Now imagine each grain is a star. That's closer to the scale we're talking about. And that's just one galaxy. There are likely hundreds of billions of galaxies in the observable universe, each filled with billions of stars. Around many of those stars are planets, and on some of those planets, the conditions could be just right. Not too hot, not too cold. Liquid water, the basic ingredients for life. So here's the quiet question that keeps scientists awake at night. If the universe has so many chances to create life, why haven't we seen anyone? This puzzle has a name. It's called the Fermi paradox. The story goes like this. In 1950, a physicist named Enrico Fermi was having lunch with colleagues. They were casually talking about space, aliens, and the possibility of life beyond Earth. Fermi listened for a while, then simply asked, "Where is everybody?" That was it. Just that. Because when you really think about it, the math seems to suggest that life should not be rare. The universe is about 13.8 billion years old. That's almost 3 times older than Earth. If the age of the universe were compressed into 1 calendar year, Earth would not even form until early September. Humans would appear in the last few minutes before midnight on December 31st. So if life started here fairly quickly, after Earth cooled down, could it have started somewhere else much earlier? And if it started earlier, would that civilization not have had millions or even billions of years to grow, to invent, to explore, to expand? Even if intelligent life is rare, even if only 1 in a million planets produces advanced beings, there should still be thousands, maybe millions, of advanced civilizations in our galaxy alone. So where are they? Why haven't we seen giant alien structures orbiting stars? Why haven't we detected clear signals? Why hasn't a probe or spacecraft arrived in our solar system? Is everyone hiding? Or is there something we don't understand? Maybe space is simply too big. Maybe travel between stars is much harder than we imagine. Maybe advanced civilizations destroy themselves before they get far. Or maybe we are early. So early that the galaxy is still mostly quiet. But before we jump to answers, it helps to sit with the question. Imagine walking into a massive city at night. Every building is dark, no lights in the windows, no cars, no sound, just empty streets stretching for miles. Wouldn't that feel strange? Now imagine that city has billions of buildings. That's what the universe feels like right now. We've been listening for signals for decades. Powerful radio telescopes have scanned the sky. We've sent messages out. We've launched spacecraft with golden records attached, like messages in bottles drifting across a cosmic ocean. And still, nothing clear has come back. Silence. But silence does not always mean absence. If you stand in the middle of a desert, you might hear nothing. But that doesn't mean life does not exist elsewhere on Earth. It just means you are far from it. So could that be our situation? Are we simply too far apart? Or are civilizations separated not just by space, but by time? Maybe someone lived millions of years ago in another part of the galaxy. They rose, explored, and vanished long before humans learned to make fire. And maybe another civilization will rise millions of years from now, long after we are gone. 2 candles burning at different times in a vast dark room, never overlapping. It's also possible that intelligence is far rarer than we think. Life on Earth began almost as soon as conditions allowed it. Simple cells appeared relatively quickly, but complex life, animals, brains, tools, that took billions of years. For most of Earth's history, life was microscopic. For about 3 billion years, nothing more complicated than tiny single cells existed. That's like waiting 3/4 of the entire age of the Earth just to get something bigger than a grain of rice. So maybe simple life is common, but advanced life, that might be a different story. And then there's another quiet thought. Maybe they are out there. Maybe they are listening, just like we are. And maybe they are asking the exact same question, looking at their own night sky, scanning their own galaxy, wondering why it feels so empty. There's something humbling about this paradox. It reminds us that we are still very new to this search. We've only been using radio for about 100 years. That's a blink of an eye compared to cosmic time. If the universe were as old as a full day, we've been listening for less than a single second. Is that really long enough to expect an answer? Probably not. And yet the silence feels meaningful. It pushes us to think deeper about physics, biology, survival, and the limits of technology. Because maybe the reason aliens haven't reached Earth isn't about them at all. Maybe it's about the universe itself. Maybe there are barriers we haven't fully understood yet. Limits built into space and time, obstacles so vast that even the most advanced beings must bow to them. As we gently explore this question, we'll move through those possibilities one by one. Not in a rush, just calmly, patiently. Because the universe moves slowly, and sometimes the most powerful answers are not loud. They are quiet, just like the night sky. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. Before we wonder why no one has arrived, we need to understand the stage where all of this is happening. Our home galaxy, the Milky Way, is enormous. It stretches about 100,000 light years from one side to the other. A light year is the distance light travels in 1 year, and light moves incredibly fast, about 300,000 kilometers every second. That's fast enough to circle the Earth about 7 times in a single second. So in 1 second, light could wrap around our planet 7 times. In 1 minute, it could travel from Earth to the Moon and back more than once. In 1 year, it travels nearly 9.5 trillion kilometers. And our galaxy is 100,000 of those years across. If that number feels slippery in your mind, that's normal. It's too large for daily experience. So let's shrink it down. Imagine the Milky Way scaled down to the size of North America, from one coast to the other. If that were the case, our entire solar system, including the orbit of Pluto, would be smaller than a coin placed on a sidewalk. That's how tiny we are compared to the galaxy. Now here's a quiet question. If an alien civilization lived on the opposite side of the Milky Way, how long would it take them to reach us? Even if they could travel at the speed of light, which as far as we know, nothing with mass can do, it would still take 100,000 years to cross from one end to the other. 100,000 years. That's longer than all of recorded human history. Human civilization, with cities and writing, is only about 5,000 years old. If you stacked all of human civilization into a timeline, crossing the galaxy at light speed would take 20 times longer than everything we've ever built. And that's at light speed. But no spacecraft we have today comes even close. Our fastest spacecraft, the Parker Solar Probe, moves at about 700,000 kilometers per hour. That sounds incredibly fast. Faster than any plane or bullet. But compared to light, it's crawling. At that speed, crossing the galaxy would take tens of millions of years, longer than humans have even existed as a species. So when we ask, why haven't they come here? Maybe we should ask another question. How easy is it to travel across something that vast? The Milky Way isn't just wide, it's also filled with structure. There are spiral arms made of gas and dust, dense star clusters, regions of radiation, empty stretches that span thousands of light years. Picture walking across a continent. Now imagine that continent is 100,000 times wider than Earth, and you have no roads, no map, just scattered islands of light in a dark ocean. Even sending a simple message across those distances takes time. If a civilization 50,000 light years away sent us a greeting today, we wouldn't receive it for 50,000 years. And if we replied instantly, they wouldn't get our answer for another 50,000 years. That's a full 100,000-year conversation cycle. Would any society plan around that kind of delay? It's hard to imagine. Sometimes people wonder, but couldn't a highly advanced civilization spread slowly, even at low speeds? Yes, that's possible. If a civilization could travel at just 1% of the speed of light, which is still far beyond our current ability, it would take about 10 million years to cross the galaxy. 10 million years sounds enormous, but in cosmic terms, it's not that long. The Milky Way is over 13 billion years old. 10 million years is less than 1/10 of that time. If the galaxy were the age of a 100-year-old person, 10 million years would be less than a single day. So here's the strange part. If even one civilization started expanding millions of years ago, and if they kept going steadily, they could have reached every corner of the galaxy by now, including us. And yet, we see no clear sign, no giant energy structures around stars, no alien ships drifting between systems, no unmistakable signals, just quiet stars. So what does that mean? Maybe expansion isn't as simple as it sounds. Maybe crossing even small portions of the galaxy is far more difficult than our imagination suggests. It's easy to say the galaxy as if it's a place you could drive across, but the reality is closer to crossing an ocean so wide that even light, the fastest thing in existence, needs 100,000 years to make the trip. If you imagine sending a spacecraft today, and knowing that it would not arrive until long after your entire civilization has changed beyond recognition, would you still go? Would the motivation survive the timescale? And what about risk? What about uncertainty? When distances stretch beyond 100,000 light years, small problems become enormous ones. Tiny navigation error could mean missing your target star by trillions of kilometers. A small system failure could leave a ship drifting for eternity. The scale alone introduces a kind of silence. Even if life is common, even if intelligence arises often, the Milky Way might simply be too big for neighbors to easily meet. It's like living in a forest so wide that two intelligent species could exist on opposite sides and never cross paths. Not because they are hiding, not because they don't want to meet, but because the forest is vast beyond belief. When we look at the night sky, it feels intimate. Stars twinkle gently. They seem close enough to touch. But the truth is more humbling. Each of those tiny points of light may be separated by distances so large that even light itself takes years, centuries, or millennia to travel between them. And we are just one small system, orbiting an ordinary star, sitting quietly in one spiral arm of a galaxy that stretches farther than the mind can comfortably hold. Maybe before asking why aliens haven't reached Earth, we need to fully feel just how far here really is. If the galaxy feels vast, what about just the distance to the very nearest star? Surely that must be manageable. After all, when we look at the night sky, the stars don't seem that far apart. They sparkle softly, almost like small lights placed on a dark ceiling. But that feeling is an illusion. The closest star system to us is called Proxima Centauri. It is about 4.2 light years away. That number might sound small compared to 100,000 light years across the galaxy. Just 4 light years. It feels almost comforting. But let's slow down and look at what that really means. Light travels at about 300,000 kilometers every second. That's fast enough to circle Earth 7 times in a single second. Now imagine light racing forward non-stop, every second, every minute, every day, for over 4 years. That's how far away Proxima Centauri is. If you tried to drive that distance in a car going 100 kilometers per hour without ever stopping, it would take you more than 40 million years to get there. That's longer than humans have existed as a species. Even our fastest spacecraft would struggle. The Voyager 1 probe, which has been traveling since 1977, is moving at about 60,000 kilometers per hour. At that speed, reaching Proxima Centauri would take roughly 70,000 years. 70,000 years. That's longer than all of recorded human history combined. When Voyager was launched, disco music was popular, and the internet didn't exist. And yet, even after nearly 50 years of travel, it has not even come close to leaving our local neighborhood of space. So here's a gentle question. If we can't easily reach the closest star, how likely is it that someone else has casually reached us? Interstellar space, the space between stars, is not like crossing a city or even crossing an ocean. It's more like crossing an endless desert, where every step forward still leaves you surrounded by emptiness. Imagine shrinking our solar system down so that the sun is the size of a basketball placed in the center of a large city park. Earth would be a small bead a few dozen meters away. Neptune would be near the edge of the park. Now, where would Proxima Centauri be in that scale? It would not be in the same park. It would be thousands of kilometers away, closer to another continent. That's the kind of separation we're dealing with. So when we imagine alien visitors, we often picture sleek ships gliding between stars, as if they were neighboring towns. But the reality is more like crossing entire continents of emptiness, just to reach the next tiny island of light. And there's another quiet thought. Stars are not standing still. They move through the galaxy, orbiting its center. Proxima Centauri will not always be our nearest neighbor. Over millions of years, the distances shift. Some stars drift closer, others drift away. But even at their closest, we are still talking about trillions upon trillions of kilometers. So could an advanced civilization overcome this? Maybe. They might build ships that travel at a significant fraction of the speed of light. At 10% of light speed, the journey to Proxima Centauri would take about 40 years. 40 years feels manageable compared to 70,000. It's about the length of a career, about half a lifetime. But reaching 10% of light speed is not a small challenge. It requires energy and engineering far beyond what we can currently achieve. And even then, you must slow down when you arrive. Accelerating is only half the journey. Decelerating requires just as much effort. You can't simply speed toward a star and hope to gently drift into orbit. At those speeds, missing your target by even a tiny angle would mean flying past it forever. So if aliens exist on a planet orbiting Proxima Centauri, they would face the exact same problem in reverse. To reach us, they would need to build something capable of traveling for decades, perhaps centuries. Through deep space, they would need to survive radiation, system failures, and the psychological strain of distance, all just to reach a small, pale planet orbiting an average yellow star. Would they consider that worth the effort? Maybe, but maybe not. We sometimes assume that advanced life would naturally want to explore. After all, humans crossed oceans, climbed mountains, and walked on the moon. But even our boldest journeys were tiny compared to interstellar space. Crossing the Atlantic Ocean is about 5,000 kilometers. That's like taking a few steps across a room, compared to the trillions of kilometers between stars. And there's something else to consider. We have only been able to detect exoplanets around other stars for a few decades. Before that, we didn't even know if planets were common. If another civilization is watching us from Proxima Centauri, Would they easily detect Earth as a living world? Or would we just look like a faint, distant dot, lost in glare? The nearest star problem reminds us that even neighbors in cosmic terms are unimaginably far apart. When you stand under the night sky and see a bright star, it feels close, familiar, almost friendly. But between us and that light lies a distance so great that even our fastest machines would take tens of thousands of years to cross it. So maybe the silence isn't surprising. Maybe the real surprise would be if anyone had managed to bridge that gap at all. And we haven't even left our own solar system yet. When we talk about traveling between stars, there is one limit that quietly stands in the way. It's not about fuel. It's not about engineering. It's not even about courage. It's about the speed of light. Light moves at about 300,000 kilometers per second. In the time it takes you to blink, light could travel from one side of Earth to the other several times. If you could move that fast, you could circle the planet more than 7 times in a single second. Nothing we know moves faster, and according to our best understanding of physics, nothing with mass can move faster. This idea comes from Einstein's theory of relativity, but you don't need complex math to feel what it means. Imagine pushing a heavy car. At first, it's hard to move. Then it rolls a little easier, but the faster you try to push it, the harder it becomes to make it go even faster. Now imagine that effect increasing more and more as speed increases. The closer you get to the speed of light, the more energy you must pour in just to gain a tiny bit more speed. It's like trying to run toward a finish line that keeps moving away from you. At 50% of light speed, you need an enormous amount of energy. At 90%, you need far more. At 99%, the energy required becomes almost unimaginable. And to actually reach 100%, the required energy becomes infinite. Infinite. That's not just difficult, that's impossible. So even the most advanced alien civilization would face this wall. No matter how clever they are, no matter how advanced their technology, the speed of light appears to be a built-in speed limit for the universe. But why would the universe have a speed limit at all? It feels strange, doesn't it? On Earth, if you want to go faster, you build a stronger engine, a faster plane, a better rocket. There's always some way to improve. But space itself seems to say, this is as fast as anything can go. And that limit has deep consequences. If nothing can exceed light speed, then even the closest stars remain years away. The center of our galaxy remains tens of thousands of years away. Other galaxies remain millions or billions of years away. It's as if the universe is stitched together with distance that cannot be rushed. Some people wonder, what about warp drives, wormholes, science fiction ideas? They're fascinating to imagine. A ship bending space like folding a sheet of paper, traveling vast distances instantly. But here's the calm truth. We have no evidence that such things are possible in practice. Some ideas appear in equations, but they require exotic forms of matter we've never observed. Matter with negative energy. Materials that may not even exist. So for now, light speed remains the boundary. And even reaching close to that speed would require technology and energy far beyond what we can currently imagine. This changes the way we think about alien visits. If an advanced civilization exists 1,000 light years away, even traveling at 90% of light speed, it would still take over 1,100 years to reach us. That's longer than the time since the fall of the Roman Empire. Would a society plan a journey that long? Would they send travelers who know they will never see home again? Maybe, but it would not be casual. And here's something else interesting. Light speed doesn't just limit travel. It also limits communication. When you send a message, even a simple radio signal, it travels at light speed, no faster. If a civilization 500 light years away heard our first radio broadcasts from the early 1900s, they wouldn't receive them until the year 2400. And if they replied immediately, we wouldn't hear back until the year 2900. A full 1,000 years for a single exchange. So even if intelligent life is out there, we may simply be too far apart to notice each other in any practical way. The speed of light shapes everything. It keeps stars separated. It keeps galaxies distant. It keeps civilizations isolated. Imagine living in a world where the fastest possible ship could only travel 10 kilometers per hour. No matter how much you improved your technology, you could never go faster. Oceans would feel endless. Continents would remain cut off. Whole cultures might never meet. That's similar to what the speed of light does to the universe. It stretches space into islands, separated by deep oceans of time. And so when we ask why haven't aliens reached Earth, we have to remember this invisible rule. Even if they exist, even if they want to explore, they cannot simply leap across the stars. The universe does not allow shortcuts easily. And perhaps that is part of the answer. Not that aliens are hiding, not that they are uninterested, but that the fabric of space itself sets a limit, a calm, quiet limit, one that even the brightest civilization must respect. And so the stars remain where they are, far apart, shining patiently, separated by a speed that cannot be broken. The speed of light does more than limit how fast you can travel. It also changes time itself. That sounds dramatic at first, but it's not science fiction. It's something we have measured, something that satellites must account for every day. When objects move very fast, especially close to the speed of light, time slows down for them, not in a poetic way, not in a feels slower kind of way. It literally passes more slowly. Imagine two identical clocks. One stays on Earth, the other boards a spaceship that travels near the speed of light for many years, then comes back. When the ship returns, the traveling clock will show less time has passed. The astronaut may have aged only 10 years. Meanwhile, 20, 50, or even hundreds of years might have passed on Earth, depending on how fast they traveled. It's called time dilation. And it raises a strange thought. If an alien civilization could travel at 99% of the speed of light, a journey that takes 100 years from our point of view might feel much shorter to them. Maybe only a few years pass on their ship. So does that solve the problem? Could aliens simply outrun time? Not quite, because even if time feels slower to the travelers, the outside universe keeps moving forward. If someone traveled 1,000 light years at near light speed, they might experience only a few decades on board. But from Earth's perspective, 1,000 years would still pass. That means they would arrive in a completely different era. If aliens left their home 5,000 years ago aiming for Earth, by the time they arrived, their home civilization might have changed beyond recognition. It might not even exist anymore. And Earth would also have changed. When humans were building pyramids, if a signal had been sent from a distant world, we would not receive it until thousands of years later. And when we replied, they might be gone. So even with time dilation helping the travelers, the universe does not let both sides stay synchronized. It's like writing a letter to someone who lives in a town so far away that by the time your letter arrives, the town has already transformed. New buildings, new language, new people you might never truly meet in the same moment. There's also a practical question. If time slows down for travelers, what happens when they return home? Suppose an alien crew travels 2,000 light years and back at near light speed. For them, maybe 50 years pass. But on their home planet, 4,000 years may have gone by. They would return to a civilization they no longer recognize. Different culture, different technology, possibly even a different species if evolution has continued. Would that risk discourage long-distance travel? Maybe. And then there's the emotional side. Humans care about connection, about family, about shared time. Would another species feel the same? If leaving your planet means losing everything familiar forever, because centuries or millennia will pass while you're gone, would that change your decision? Time dilation makes interstellar travel stranger, not simpler. It protects the travelers from aging too quickly, but it does not protect relationships, cultures, or continuity. And there's another layer. The faster you move, the more extreme time dilation becomes. But reaching those speeds requires enormous energy, so you're trading one difficulty for another. More speed means less time experienced on board, but more speed also means vastly more energy required. And even then, outside time marches on. There's something quietly isolating about this. The universe is not just large in space, it is large in time. Stars are born and die over millions or billions of years. Civilizations might rise and fall in a few thousand. The overlap between two intelligent species might be incredibly small. It's possible that somewhere in the galaxy, a civilization existed 2 million years ago. They might have looked at the stars and wondered the same thing we do. But by the time humans appeared, they were already gone. And millions of years from now, another civilization might arise after we are long gone. Two lights that never shine at the same time. Time dilation reminds us that even if travel is technically possible, coordination is fragile. You might reach another star system, only to find it empty because its intelligent life ended 100,000 years earlier. Or you might arrive too early, before intelligence has developed. The universe does not guarantee timing. It does not pause to let civilizations meet. It simply unfolds at its own pace. And so when we ask why aliens haven't reached Earth, part of the answer might lie in time itself. Not just distance, not just speed, but timing. Maybe the galaxy is not empty. Maybe it's just out of sync. And in a universe where time stretches and bends, even the most advanced travelers cannot control when they arrive in someone else's story. Even if a civilization accepts the distance, even if they accept the time problem, there is another quiet obstacle waiting in the background. Energy. To move something through space is not just about building a strong ship. It's about pushing that ship faster and faster. And the faster you want to go, the more energy you must use. Let's think about something simple first. When you ride a bicycle slowly, it doesn't take much effort. When you try to sprint as fast as you can, your legs burn quickly. Speed demands energy. Now imagine this effect not just doubling, but increasing again and again as you approach the speed of light. If you wanted to accelerate a small spacecraft, let's say the mass of a large airplane, to even 10% of the speed of light, the energy required would be enormous. To give you a comparison, the total energy used by all of humanity in one entire year, every car, every plane, every power plant, every home, would not be enough to send a large spacecraft to near light speed. And that's just one ship. If an alien civilization wanted to send fleets, or colonists, or heavy equipment, the energy demand would grow beyond imagination. At higher speeds, the energy doesn't just increase steadily, it grows dramatically. Reaching 50% of light speed takes far more than 5 times the energy of reaching 10%. Becomes a steep climb. You can picture it like trying to lift a weight. Lifting 10 kilograms feels manageable. Lifting 20 kilograms feels heavier. But lifting 1,000 kilograms is not just 10 times harder. It becomes nearly impossible without special machinery. Speed works in a similar way, and here's something else to consider. You don't just need energy to speed up, you also need energy to slow down. If you accelerate halfway to your destination, you must spend the second half of the journey decelerating. Otherwise, you would simply fly past your target star and continue drifting into deep space. So the total energy cost doubles. Now imagine a civilization thinking carefully. Would they choose to spend the equivalent of their entire planet's energy output for decades just to send a small group of travelers across interstellar space? Maybe, but they would need a strong reason. We sometimes assume that advanced civilizations would have unlimited energy, but even stars themselves have limits. Our sun produces an enormous amount of energy every second, enough to power human civilization millions of times over. Yet even the sun is finite. It will shine for about 10 billion years in total. It is already almost halfway through its life. If you tried to harness a large fraction of a star's energy, you would need structures on a scale we can barely imagine. Picture building solar panels, not across a field, not across a country, but around an entire star, encircling something 1.4 million kilometers wide. That's about 100 times wider than Earth placed side by side. The engineering challenge alone is staggering. So here's a gentle question. If interstellar travel requires energy on a planetary or even stellar scale, how many civilizations could realistically afford that? Maybe only the very most advanced. And even then, would they use that energy for travel or for something else? Energy can be used to power cities, to build habitats, to simulate entire worlds digitally, to extend life, to improve comfort and stability. Would exploration across vast, empty space be the priority? We assume curiosity would drive them outward. After all, humans crossed oceans despite great cost. But even crossing Earth's oceans is tiny compared to crossing space. The energy required to sail across the Atlantic is like lighting a campfire compared to the energy required for interstellar travel, which would be more like powering a continent. There's also the risk factor. If a mission fails halfway through, all that energy is lost. Decades of effort, generations of planning. Would societies repeatedly take such risks? Or would they decide that staying home is wiser? Perhaps advanced civilizations turn inward instead of outward, using their energy to build virtual realities, to explore inner worlds of thought and simulation, to create experiences more vivid than physical travel. If you could build entire universes inside powerful computers, would you still feel the need to physically cross the stars? It's an interesting possibility. Maybe the silence we observe is not because civilizations are absent, but because the cost of moving physical matter across space is simply too high. Space is not like flying across a planet. It is not like sailing to a nearby island. It is pushing against the fundamental limits of energy itself. And the universe does not give discounts. Every increase in speed demands more. Every kilogram of mass adds to the cost. Every mistake multiplies the loss. So when we quietly ask why aliens have not reached Earth, energy may be part of the answer. Not fear, not hostility, not secrecy, but simple physics, the kind that applies equally to us and to any civilization, no matter how intelligent. The stars may be within sight, but reaching them might require more power than most worlds are ever willing or able to spend. Even if a civilization finds the energy, even if they are willing to spend it, there is another quiet obstacle that makes interstellar travel even harder. It's something called the rocket equation. The name sounds technical, but the idea is simple. To move forward in space, a rocket must throw mass backward. That backward push creates forward motion. When you let air out of a balloon and it shoots across the room, that's the same principle. Air rushes out one way, the balloon moves the other way. But here's the catch. To carry fuel, you need mass. And to push more mass, you need more fuel. And to carry that extra fuel, you need even more fuel. It becomes a chain reaction. Imagine trying to carry water across a desert. You need water to survive the trip. But the more water you carry, the heavier your load becomes. So you need more energy to move. That means you need even more water. Soon, you're mostly carrying supplies just to carry supplies. That's what rockets face. If you want to go faster, you need more fuel. But adding more fuel increases the ship's weight. So you need even more fuel to push that extra weight. The math behind this grows quickly, not slowly, not steadily, but dramatically. To double your speed, you don't just double your fuel. You might need several times more, and as you approach higher speeds, especially fractions of light speed, the fuel requirements become enormous. Imagine building a spaceship the size of a large building. Now imagine that 90% of its total weight is just fuel. The crew, the equipment, the structure itself, all squeezed into the remaining 10%. That's already how modern rockets work. When we launch a rocket from Earth, most of what you see is fuel, the actual payload at the top. Satellites, probes, astronauts is only a small fraction. Now imagine trying to reach another star. To accelerate to even 10% of the speed of light, using traditional rocket fuel would require a fuel mass so large that the ship itself would be tiny in comparison. It would be like building a train where almost every single car is just fuel, and the passengers fit into a small cabin at the very front. And remember, you must slow down at the destination. That means you need fuel for braking too, so the fuel requirement multiplies again. At some point, the rocket becomes mostly fuel, carrying more fuel to burn later. And this is with chemical rockets. Could advanced civilizations use something better? Possibly. They might use nuclear propulsion, fusion engines, matter-antimatter reactions. These methods release far more energy per kilogram of fuel. But even then, the rocket equation still applies. You still must carry reaction mass, unless you invent entirely new physics, and carrying mass across interstellar space is costly. There's another detail people often overlook. When you launch from Earth, gravity helps hold you down. You must fight against it. In deep space, you don't have to fight gravity the same way. That helps. But the rocket equation still governs acceleration and deceleration. It doesn't disappear just because you're far from a planet. So here's a quiet question. If the fuel mass grows so quickly with speed, how practical is interstellar travel for large ships? Could small probes make the journey? Possibly. Tiny machines with minimal mass require less fuel. But sending biological beings, sending cities, sending colonies, that's a different scale entirely. It's like comparing mailing a letter to moving an entire town across an ocean. One is manageable, the other requires fleets of ships and enormous resources. The rocket equation makes large-scale expansion much harder than it first appears. Even if a civilization wants to explore, they might start by sending small robotic probes. Machines don't need air, they don't need food, they don't get bored, and they can be much lighter. But even then, the distances remain vast, and the fuel requirements still climb steeply as speed increases. The deeper truth here is that the universe seems to resist rapid movement of heavy things. Photons, particles of light, can travel at light speed because they have no mass. But as soon as you add mass, the difficulty rises sharply. It's as if space itself becomes thicker the faster you try to move through it. So when we ask why aliens haven't reached Earth, we must consider this quiet engineering wall, not just energy, not just distance, but the way fuel and mass interact. The galaxy might not be empty. It might simply be that moving physical bodies between stars is so expensive, so complex, and so heavy with requirements that very few civilizations are tempted. And those that do may send only small, quiet machines that are hard to detect, machines that drift silently between stars, taking thousands of years to arrive. The rocket equation reminds us that interstellar travel is not just about bravery or intelligence. It's about weight, and the universe makes weight matter a lot. Let's imagine for a moment that a civilization solves the fuel problem. They build a powerful engine. They design a ship strong enough to survive for decades or centuries. There is still something waiting in the dark between stars. Radiation. When we think of space, we often picture emptiness, a silent vacuum, calm and still. But interstellar space is not completely empty. It is filled with tiny particles moving at incredible speeds, high-energy protons, atomic nuclei, radiation from distant stars, and exploding supernovae. These particles are called cosmic rays, and they are not gentle. On Earth, we are protected by two shields: the atmosphere above us, which is about 100 kilometers thick, and Earth's magnetic field, which stretches tens of thousands of kilometers into space like an invisible bubble. If you stacked the atmosphere like layers of blankets, it would be like wrapping the planet in a thick protective coat. Most harmful radiation never reaches the ground, but in deep space, there is no atmosphere, no natural magnetic shield, unless you build one. Astronauts on the International Space Station already experience more radiation than people on Earth, and that station is only about 400 kilometers above the surface, roughly the distance of a short airplane flight compared to crossing a continent. Imagine leaving that safe zone entirely. Imagine traveling for decades beyond the sun's protective influence. Cosmic rays move close to the speed of light. When they hit living tissue, they can damage DNA. Over time, that damage increases the risk of cancer, organ failure, and other health problems. So how serious is it? On a long journey to Mars, which takes about 6 to 9 months, radiation exposure is already a major concern. And Mars is right next door compared to the stars. Proxima Centauri is over 4 light-years away. Even at 10% of light speed, the journey would take about 40 years. 40 years of constant exposure. That's like living your entire adult life inside an X-ray machine. Unless you bring heavy shielding. But shielding adds mass. And as we've already seen, more mass means more fuel. So now we face a trade-off. Build thicker walls to protect against radiation, but then you need more energy to push that extra weight. Or build a lighter ship and accept higher radiation risk. Advanced civilizations might develop powerful magnetic shields to deflect charged particles. They might use water or dense materials as protective layers. Water is actually very good at absorbing radiation, but carrying thousands of tons of water across interstellar space would be like trying to push a small mountain. Imagine filling an Olympic swimming pool, about 2.5 million liters of water, and then trying to accelerate all of it to high speed. That's the kind of scale we're talking about for serious shielding. And radiation is not constant and predictable. Sometimes distant stars explode as supernovae. When they do, they send bursts of radiation across the galaxy. If a ship were in the wrong place at the wrong time, it could be exposed to sudden spikes. Even solar flares from our own sun can be dangerous. That's why astronauts monitor space weather carefully. In interstellar space, you lose that early warning system. So here's a quiet question. Would a biological species choose to risk multi-decade exposure to unpredictable radiation? Maybe they would send machines instead. Machines don't get cancer. They don't have DNA to damage. Radiation can still harm electronics, but hardened systems can be built to resist it. And yet, even machines degrade over time. High-energy particles can flip bits in computer memory. They can slowly weaken materials. Over decades or centuries, small errors can accumulate. Interstellar travel isn't just about reaching the destination. It's about surviving the journey intact. There's something else interesting. The faster you go, the more dangerous radiation becomes. Why? Because at high speeds, particles hitting your ship carry even more energy. It's similar to how a small pebble can crack a windshield if your car is moving fast enough. If you're walking slowly and a raindrop hits you, it feels soft. If you're riding a motorcycle at high speed in the rain, those same drops can sting sharply. Speed turns tiny things into threats. So a ship traveling at a significant fraction of light speed would not just face cosmic rays from all directions, it would also experience intensified impacts from particles in its path. The universe between stars may be thin compared to air on Earth, But over light years of distance, even thin gas adds up, and radiation is constant, invisible, silent, persistent. It doesn't explode loudly. It simply works slowly day after day. So perhaps this is another reason the galaxy feels quiet, not because civilizations do not exist, but because the space between stars is not friendly to fragile biological life. The journey might be so harsh that only the most determined or the most advanced would attempt it. And even then, it would require careful design, massive protection, and long preparation. When we look up at the stars, they seem calm and beautiful. But between them lies an ocean not of water, but of radiation. And crossing that ocean safely is far more difficult than it first appears. Even if a ship is protected from radiation, even if it has enough energy, there is something else waiting quietly in deep space: dust. That might sound harmless at first. After all, dust on Earth is soft. It settles on shelves. It floats gently in sunlight. But in space, dust behaves very differently. Interstellar space is not completely empty. It contains tiny grains of material, bits of carbon, silicates, frozen gases. Most of them are smaller than a grain of sand. Many are smaller than a grain of pollen. Individually, they are almost nothing. But speed changes everything. Imagine holding a small pebble in your hand. It feels light, harmless. Now imagine that same pebble fired from a high-speed rifle. Suddenly, something small becomes dangerous. In space, if a spacecraft is traveling at 10% of the speed of light, that's about 30,000 kilometers per second. Even a tiny grain of dust becomes a high-energy projectile. At that speed, crossing from New York to Los Angeles would take less than a second. Now picture hitting a speck of dust at that speed. The energy released in that tiny collision could be like a small explosion. It wouldn't just leave a scratch. It could punch through shielding. And remember, this wouldn't be a one-time event over a journey of 4 light years to the nearest star. A ship would pass through trillions upon trillions of cubic kilometers of space, even though the dust is sparse, far thinner than air. Over such extreme distances, impacts become inevitable. It's like driving a car through light rain for 5 minutes. You might only see a few drops, but drive through that rain non-stop for 40 years at extreme speed, and even tiny droplets start to matter. There's a simple comparison that helps. If you were standing still and someone gently tossed a grain of sand at you, you might barely notice. But if you were riding a motorcycle at 200 kilometers per hour and that same grain hit your skin, it would sting sharply. Now multiply that speed thousands of times. At relativistic speeds, speeds close to light speed, the kinetic energy of even a microscopic particle becomes huge. So how could a civilization protect against that? One idea is to build thick shielding at the front of the spacecraft. Layers of metal, composite materials, maybe even fields of charged particles to deflect incoming debris. But again, thicker shielding means more mass. More mass means more fuel. And even the thickest shield cannot be infinitely thick. Another idea is to place a cloud of small particles in front of the ship, acting like a protective buffer. Incoming dust would collide with that cloud first, breaking apart before reaching the main hull. It's clever, but it requires precise engineering and constant replenishment. And there's something else. The faster you go, the worse the problem becomes. At slower speeds, say 1% of light speed, dust impacts are still dangerous, but more manageable. At 20% or 30% of light speed, the energy released in each collision increases dramatically. Speed is both a solution and a danger. Go slower, and the journey takes centuries or millennia. Go faster, and the environment becomes more violent. There is also the unknown factor. We don't have detailed maps of interstellar dust clouds between every star. Some regions are denser than others. A ship traveling blind might enter an area with higher particle concentration. It's like flying a plane through a clear sky, not knowing a storm lies ahead. Over millions of kilometers, the risk grows. So here's a quiet question. Would it be wiser for an advanced civilization to send tiny probes instead of large crewed ships? Small probes have less surface area, less mass, less risk. If one is destroyed, the loss is limited. But sending biological beings across such distances, at such speeds, through an environment filled with invisible hazards, that's a different scale of risk. Interstellar dust may be sparse, but over light years, sparse becomes significant, and there's something almost poetic about this. The universe does not block the path with giant walls. It doesn't place huge barriers between stars. Instead, it fills the darkness with countless tiny obstacles, small grains, nearly invisible. But at high speed, even the smallest things become powerful. It's like the universe whispering, "You may travel, but not carelessly." So when we ask why aliens haven't reached Earth, perhaps part of the answer lies in these tiny grains drifting silently between stars. They are not dramatic, they are not obvious, but they turn speed into danger. And over distances measured in light years, distances so vast that even light needs years to cross them, even dust becomes a serious challenge. The space between stars may look empty, but it is not gentle. And crossing it safely is far more complicated than simply pointing a ship toward a distant sun and pressing forward. Let's imagine that a civilization accepts the distance. They know the journey will take hundreds, maybe thousands of years. They decide not to race toward light speed. Instead, they choose a slower, steadier path. What if they build a ship meant to last for generations? Not a short mission, not a single lifetime, but a moving world. This idea is called a generation ship. Picture a spacecraft so large that it contains farms, homes, water systems, and entire communities inside. Children are born on the ship. They grow up knowing nothing but the artificial sky above them. They grow old and pass away before the ship ever reaches its destination. Their grandchildren continue the journey, and maybe their great-grandchildren finally arrive. It sounds almost romantic at first, a traveling civilization crossing the stars. But when you slow down and think about it, questions begin to appear. How large would such a ship need to be? A few dozen people would not be enough. Genetic diversity matters. To avoid serious health problems over generations, you would need hundreds, maybe thousands of individuals. Imagine a small town placed inside a rotating cylinder in space. The cylinder might need to be several kilometers long enough to hold farmland and living areas. That's like fitting an entire neighborhood inside a giant metal tube drifting between stars. And it must function perfectly for centuries. No resupply, no outside help, no repair shop around the corner. Every system must be self-sustaining. Water must be recycled endlessly. Air must be cleaned continuously. Food must be grown reliably year after year. We struggle to maintain ecosystems on Earth even with the entire planet supporting us. Now imagine trying to keep a closed system balanced inside a ship, the size of a small city. Even tiny imbalances could grow over time. What if a disease spreads? What if crops fail? What if mechanical systems slowly degrade? A journey lasting 500 years means trusting that the structure will survive longer than many nations have existed. And then there is the human side. Would future generations feel committed to the mission? Imagine being born on that ship. You did not choose to leave your home planet. You did not choose this journey. Yet your entire life is shaped by a decision made centuries ago. Would everyone agree to continue? What if, after 200 years, the community decides they no longer want to travel, that they prefer to stay where they are, drifting through space? Social stability becomes just as important as engineering. We know from history that societies change quickly. Governments rise and fall. Beliefs shift. Conflicts emerge. On Earth, if a nation collapses, people can migrate, they can trade, they can seek help. On a generation ship, there is nowhere else to go. It is a closed world. Small disagreements could grow into serious divisions. Maintaining harmony over centuries would require careful planning. And there is another quiet question. Would the original destination still be worth reaching? If the journey takes 1,000 years, by the time the ship arrives, technology back home might have advanced far beyond what the travelers carry. Imagine leaving Earth in the year 1000 with the best technology of that time. Wooden ships, simple tools, aiming to reach another continent over centuries. Meanwhile, those who stayed behind eventually invent airplanes and cross oceans in hours. The travelers might arrive only to find they were overtaken by progress. If another civilization developed faster propulsion methods later, they could send a faster ship that arrives before the original generation ship. So why risk such a long mission at all? Maybe desperation could drive it. A dying planet, a collapsing star, a need to escape, or perhaps deep curiosity. But generation ships require extraordinary patience. They require a culture that values long-term goals beyond individual lifetimes. They require trust that future generations will honor decisions made long ago. That's not impossible. Humans build cathedrals that take centuries to complete. We plant trees knowing we may never sit in their shade. But scaling that mindset to interstellar travel is something else entirely. It's like deciding to walk across an entire continent on foot, knowing that neither you nor your children will ever see the end. Would many civilizations choose that path? Perhaps some would. But even if they did, the galaxy is vast. The chance of one generation ship passing near our solar system at the right time is small. And if they are traveling slowly, maybe 1% of light speed, it would still take 400 years just to reach the nearest star. From one end of the galaxy to the other would take millions of years. That's a journey longer than human civilization has existed many times over. So maybe generation ships exist somewhere in the darkness, slowly moving, quiet, self-contained worlds drifting between suns. But their rarity, their fragility, and the immense commitment required might mean they are few. And if they are few, the odds of one arriving here at this exact moment in history become very small. Not impossible, but small. And in a universe as wide and patient as ours, small odds often mean long silence. If raising generations on a ship feels too complex, there is another idea people often imagine. What if travelers simply sleep through the journey? Not normal sleep, but deep suspended animation, a state where the body slows almost to a stop, where aging pauses, where decades can pass without the traveler feeling them. It sounds elegant. Leave your planet, enter cryosleep, wake up at a distant star. No boredom, no generational handoff, no long social struggle. Just close your eyes and arrive. But biology is not so simple. On Earth, some small creatures can survive extreme cold. Certain frogs can freeze during winter and thaw in spring. Tiny organisms called tardigrades can survive in space for short periods. But humans, and most complex life, are far more delicate. Our cells are filled with water. When water freezes, it expands. It forms ice crystals. Those crystals can tear cell membranes apart, like tiny shards of glass. To prevent this, scientists experiment with special chemicals called cryoprotectants. These reduce ice formation, but they can also be toxic in large amounts. So far, we have successfully frozen and thawed small tissues, even embryos, but freezing and reviving an entire adult human without damage remains far beyond our current ability. Now imagine doing this for not just years, but centuries. Would organs remain stable? Would memories survive? Would subtle chemical balances in the brain stay intact? Even small changes in brain structure can affect personality and memory. And memory is not just stored in one place. It is spread across billions of neurons, connected through trillions of tiny pathways. Think of the brain like a massive city of electrical wires. If even a small number of connections are altered, the pattern changes. So here's a gentle question. If you went into cryosleep and woke up 500 years later, would you truly be the same person? We don't yet know. And then there are the systems around the sleepers. Cryosleep does not remove the need for maintenance. Machines must keep running. Power must continue flowing. Temperature must remain stable for centuries. If a small system fails halfway through the journey, who repairs it? You might say, artificial intelligence could manage the ship. That's possible. But now the success of the mission depends entirely on automated systems working flawlessly for hundreds of years. Even today, electronic systems degrade over time. Materials age. Radiation slowly damages circuits. A 10-year mission is already complex. A 100-year mission is something else. A 1,000-year mission moves into almost unimaginable reliability. It's like building a clock that must tick perfectly for 1,000 years without ever being touched. Some civilizations might achieve that, but it would require extraordinary engineering. There's another quiet detail. Long-term isolation affects biology in subtle ways. Astronauts in orbit lose bone density because of low gravity. Muscles weaken. The immune system changes. And that's after just months in space. Now imagine centuries in a frozen state, followed by waking up in an entirely different gravitational environment around another star. Would the body adapt smoothly? And what about psychology? Waking up alone, in deep space, with no familiar sky, even if you are trained, the emotional shock could be immense. On Earth, humans evolved surrounded by open skies, natural cycles, fresh air. On a distant planet, light may be dimmer or redder. Days may last longer or shorter. Gravity may feel heavier or lighter. It's not just about surviving the trip. It's about remaining stable afterward. Perhaps an advanced species could engineer their biology to tolerate freezing better. They might redesign cells to resist ice damage. They might use nanotechnology to repair microscopic harm, but even then, the challenge remains large. And here is something interesting. Cryosleep solves the aging problem for individuals, but it does not solve the outside time problem. If you travel 1,000 light years at high speed and wake up decades later, 1,000 years will still have passed in the rest of the galaxy. Civilizations rise and fall in that time. You may arrive to find your destination changed or empty. So cryosleep removes boredom, but not uncertainty. It reduces the personal cost of time, but not the cosmic cost. And there's one more quiet thought. Would a highly advanced civilization even remain biological? As technology advances, species might merge with machines. They might upload their minds into digital systems. If consciousness can exist in hardware, the need for biological preservation disappears. A digital mind could be copied, stored, transmitted, and perhaps even rebuilt at the destination. In that case, cryosleep might be unnecessary. But that raises another question. If minds can be transmitted as information, maybe travel doesn't require ships at all. Maybe it becomes about sending data. And if that's the case, the problem shifts from freezing bodies to transmitting signals across light years. But signals still obey the speed of light. So even the most elegant solutions must bow to distance and time. Cryosleep sounds simple when imagined, but when examined closely, it reveals layer upon layer of difficulty. Biology is fragile. Systems must endure for centuries. Time still separates worlds. And so, once again, the silence of the stars feels less mysterious. Not because life is impossible, but because surviving the journey between stars is far more delicate than it first appears. If sending biological travelers is so difficult, if radiation, time, fuel, and fragility all stand in the way, then maybe we're imagining the wrong kind of visitor. Maybe advanced civilizations don't send living beings at all. Maybe they send machines. Think about it calmly for a moment. Machines don't need oxygen. They don't need food. They don't feel boredom. They don't suffer from loneliness in the same way biological minds do. A robotic probe can sleep for decades without complaint. It can endure radiation better than living tissue. It can be made small and light, which reduces fuel requirements. Even we, with our early technology, have already sent machines beyond our solar system. Voyager 1 and Voyager 2 are still traveling outward, carrying small golden records with messages about Earth. They are tiny compared to generation ships. Each is about the size of a small car. Now imagine what a civilization 1,000 or 1,000,000 years more advanced than us could build. They might create self-repairing machines. They might build probes powered by nuclear reactions lasting centuries. They might even design machines that can replicate themselves using local materials. This last idea is especially interesting. It's called a self-replicating probe, sometimes referred to as a von Neumann probe. The concept is simple. A machine travels to a star system. It lands on a suitable asteroid or moon. It uses local metals and materials to build copies of itself. Then those copies travel to other star systems and repeat the process. Like seeds spreading in a forest, if each probe makes just 2 copies, and each of those makes 2 more, the numbers grow quickly. 2 become 4, 4 become 8, 8 become 16. In just a few dozen generations, thousands of probes could spread outward. Even if each journey between stars takes hundreds of years, this slow expansion could fill the entire galaxy in a few million years. And in cosmic terms, a few million years is short. If the Milky Way is over 13 billion years old, a few million years is like a few days in a 100-year lifespan. So here's the quiet question. If even one civilization in the distant past built self-replicating probes, where are they? Why don't we see them mining asteroids? Why don't we detect unusual structures orbiting stars? Why hasn't one entered our solar system? You might wonder, maybe they are too small to notice. That's possible. A probe the size of a car drifting in deep space would be incredibly hard to detect, unless it came very close. Space is huge, even within our own solar system. If you placed a small object beyond Pluto's orbit, finding it would be like trying to spot a single grain of rice somewhere in a vast desert. But over billions of years, you might expect at least some sign. Unless, maybe civilizations don't build them. Why wouldn't they? One reason could be risk. A self-replicating machine that spreads across the galaxy must be perfectly controlled. If its programming has even a small flaw, it could behave unpredictably. It might consume resources endlessly. It might interfere with other life. It's similar to releasing a biological species into a new ecosystem. If it multiplies without limits, it can cause damage. Perhaps advanced civilizations are cautious. Maybe they realize that unleashing self-replicating machines could be dangerous, not just to others, but to themselves. There's another thought. Maybe machines are sent, but they are quiet observers. Instead of announcing themselves, they might watch from a distance, monitoring emerging civilizations without interfering. If you discovered a planet where intelligent life was just beginning to develop technology, would you immediately reveal yourself? Or would you observe carefully? We do something similar with wildlife. We study animals without disturbing them when possible. So perhaps probes are out there. Small, silent, patient, watching, or perhaps not. Maybe intelligence tends to turn inward. Instead of spreading physically across the galaxy, civilizations might focus on virtual worlds, artificial realities, and internal exploration. If you could create entire simulated universes inside a computer, worlds richer and more controllable than physical space, would you still feel the need to cross light years of emptiness? It's like choosing between building a rocket to visit a distant desert or designing a virtual world with infinite landscapes at the touch of a button. We don't yet know what advanced intelligence prefers, but the machine hypothesis remains strong. If travel is possible at all, it seems more practical for machines than for biology, and yet we have not clearly detected them. The sky remains quiet. No fleets of robotic harvesters, no swarms of replicating probes. So either they are extremely rare or extremely careful, or perhaps the barriers to even machine expansion are greater than we imagine. Even machines must obey the speed of light. Even machines must carry fuel or find ways to gather it. Even machines face dust, radiation, and decay. The universe is patient, but it is not forgiving. And so the question deepens. If machines are the most likely travelers between stars, and we still see nothing obvious, then maybe the silence of the galaxy is telling us something important, not about their desire, but about the difficulty of spreading at all. So far, we've been asking a simple question. If intelligent life exists out there, why hasn't it reached us? But there's another way to look at this. Maybe the real question is not about distance. Maybe it's about survival. There is an idea called the Great Filter. It suggests that somewhere along the path from simple chemistry to advanced, spacefaring civilization, there is a barrier, a stage so difficult that almost no life makes it past. Imagine the story of life as a long staircase. At the bottom step, you have basic chemistry, simple molecules forming in oceans or on rocky surfaces. Then somehow those molecules organize into self-replicating cells. That's one step. Then single cells combine into more complex cells, another step. Then multicellular life appears. Plants, animals, then nervous systems, brains, intelligence, then tool use, fire, technology, then industrial civilization, then global communication, then space travel. Each of these steps may look smooth when viewed from today, but when you slow down and examine them, each one may have been incredibly unlikely. On Earth, life began relatively quickly after the planet cooled enough to hold liquid water. That suggests the first step. Simple life might not be too rare, but for nearly 3 billion years, life remained microscopic. For most of Earth's history, there were no animals, no trees, no eyes, no minds. If you compress Earth's 4.5 billion year history into a single 24-hour day, complex animals appear only in the last 20 minutes. Humans appear in the last few seconds before midnight. That long stretch of simple life makes you wonder, was the leap to complex life extremely difficult? Was it a rare accident or just slow? And what about intelligence? Dinosaurs ruled Earth for about 165 million years, far longer than humans have existed, yet none of them built radios or rockets, so perhaps intelligence is not guaranteed. Maybe life often thrives, but rarely develops advanced tools. That could be the great filter, or perhaps the filter lies ahead of us. Maybe many civilizations reach our level. They discover electricity, they build computers, they split the atom, and then something happens. War, environmental collapse, artificial intelligence that grows beyond control, biotechnology accidents. We have existed as a technological species for only about a century. That's a blink of an eye compared to cosmic time. If civilizations typically destroy themselves within a few hundred or thousand years of becoming advanced, they may never reach the stage of interstellar travel. It's like lighting a candle in a vast dark hall, only for it to flicker out quickly. Now imagine millions of candles lighting briefly, but never lasting long enough to illuminate the entire space. So here's a quiet and personal question. Are we before the great filter? or after it? If the hardest steps are behind us, if the leap from simple cells to complex life to intelligence is incredibly rare, then we may be extraordinarily lucky. We may have already passed the most dangerous barrier. But if the great filter lies ahead, if most civilizations destroy themselves after developing powerful technology, then the silence of the galaxy becomes more unsettling, because it might mean we are approaching the same danger. There's something sobering about this idea. It shifts the focus away from aliens and toward ourselves. If we don't see evidence of advanced civilizations, maybe it's because very few survive long enough to spread. The universe is old. The Milky Way alone has been around for over 13 billion years. If civilizations commonly reached stable, long-lasting stages, even slowly spreading at a fraction of light speed, we might expect to see signs everywhere by now. The fact that we don't suggests that something stops most of them. It doesn't have to be dramatic. It could be simple instability. Imagine building a complex machine with thousands of delicate parts. If even one critical part fails, the whole system stops. Civilizations are complex machines. They rely on cooperation, resources, stable climates, and controlled technology. As power increases, so does the potential for harm. The same tools that allow us to explore space can also destroy entire cities. Maybe the leap from planet-bound civilization to stable interstellar society requires not just technology, but wisdom. And wisdom might be harder to achieve than intelligence. If that's true, the galaxy could be filled with worlds where life began, evolved, reached intelligence, and then faded. Not because space is too big, but because self-destruction is easier than long-term survival. It's a quiet possibility, and it reminds us that the silence above us may not just be about physics. It may be about choices, about how civilizations handle power, about whether curiosity and cooperation win over fear and conflict. The great filter does not have to be a single moment. It could be many small pressures adding up. And if that's the case, the reason aliens haven't reached Earth may not be that they don't exist. It may be that very few make it far enough to try. Even if a civilization survives its early dangers, even if it avoids the great filter, there is another quiet challenge. Time. Not travel time this time, but lifespan. How long does a technological civilization actually last? We often imagine advanced societies lasting for millions of years, spreading across stars, building vast structures, becoming stable and wise. But when we look at our own history, the picture feels more fragile. Human civilization, cities, writing, organized states, is only about 5,000 years old. That's like a few heartbeats compared to Earth's 4.5 billion year history. If Earth's history was stretched into a 100-kilometer road, human civilization would occupy less than the width of your hand at the very end. And even within those 5,000 years, societies have risen and fallen repeatedly. Ancient Egypt lasted thousands of years, yet it eventually faded. The Roman Empire ruled vast lands, but it collapsed. Entire cultures have disappeared due to war, disease, environmental shifts, or internal instability. Now consider technological civilization, the kind capable of radio signals and space travel. That's even younger. We've had electricity for about 150 years, nuclear weapons for less than 80 years, digital computers for about 70 years. From a cosmic perspective, that's almost nothing. So here's a gentle question. If civilizations typically last only a few hundred or a few thousand years in their advanced technological phase, is that enough time to cross the stars? Let's compare. Even traveling at 10% of light speed, far beyond our current capability, reaching a star 1,000 light years away would take 10,000 years. 10,000 years is twice as long as all of recorded human history. Would a civilization remain stable, unified, and technologically capable for that long? Maybe some could, but perhaps many do not. There are pressures, resources can run low, climate can change, political systems can fracture, technologies can outpace ethical understanding. As societies grow more powerful, the risks grow too. It's like building taller and taller towers. The higher you go, the more careful you must be with balance and structure. If even small instabilities exist, they can grow quickly. And there's something else to consider. Technological progress moves fast. In just over a century, humans went from horse-drawn carriages to spacecraft, leaving the solar system. That speed of change can be hard to manage. Cultural evolution may not always keep pace with technological power. If civilizations commonly experience unstable periods during rapid advancement, those periods might limit their lifespan. Even without dramatic self-destruction, slow decline could occur, economic collapse, loss of knowledge, fragmentation into smaller, less advanced societies. History shows that knowledge can be lost. After the fall of Rome, certain engineering techniques disappeared for centuries. If a civilization falls back technologically, interstellar projects might be abandoned. So perhaps the reason aliens haven't reached Earth is not because they lack the ability, but because few civilizations remain advanced long enough to attempt the journey. The galaxy is over 13 billion years old, but if each civilization lasts only 5,000 years in its technological phase, the chances of two civilizations overlapping in time shrink dramatically. Imagine a vast stadium where each seat lights up for just a few seconds, then goes dark again. If you walk into the stadium at a random time, you might see only darkness, even though many lights have flashed before. Civilizations could be like that, brief sparks, not permanent beacons. There's also the question of motivation over long periods. Would a civilization that has achieved stability even feel the need to expand physically? Perhaps once energy needs are met and comfort is achieved, the urgency fades. Exploration may shift from outward to inward. Virtual worlds, deep oceans, artificial habitats close to home. Interstellar travel might not feel necessary, and if the civilization does eventually decline, its unfinished projects remain incomplete. A partially built interstellar fleet might rust in orbit. A mission planned for centuries might never launch. This idea does not require disaster. It only requires impermanence. Nothing lasts forever. Stars burn out, planets cool, species evolve and disappear. Maybe technological civilizations are simply short chapters in planetary history. If so, the silence of the galaxy becomes less surprising. It's not that life never arises, it's that advanced, expansion-ready life may be rare in time, even if common in space. We might simply be living during a quiet moment, or we might be one of the few civilizations currently active. That possibility feels both humbling and heavy, because if longevity is rare, then survival becomes precious. The reason aliens haven't reached Earth may not be that they don't exist. It may be that the window during which they could reach us is narrow, and narrow windows are easy to miss in a universe that moves slowly and lasts billions of years. Let's imagine a civilization that survives. It avoids collapse. It lasts not just thousands of years, but hundreds of thousands. It becomes stable, organized, and long-lived. Even then, there is another quiet limit to consider: energy scale. A scientist named Nikolai Kardashev once suggested a simple way to measure how advanced a civilization is. Not by how intelligent it is, not by how peaceful it is, but by how much energy it can use. He proposed 3 broad levels. A Type 1 civilization can use all the energy available on its home planet. A Type 2 civilization can harness the energy of its entire star. A Type 3 civilization can use the energy of its entire galaxy. Right now, humans are not even Type 1. We use only a tiny fraction of the energy that reaches Earth from the sun. If Earth receives sunlight like a steady rainfall of power, we are only collecting a few drops. To become Type 1, we would need to capture and control energy on a planetary scale, oceans, winds, sunlight, without damaging the systems we depend on. That alone is a massive challenge. Now imagine the leap to Type 2. Our sun produces an enormous amount of energy every second, so much that in 1 second, it releases more energy than humanity has used in all of recorded history combined. To capture most of that energy, a civilization might build vast structures around its star. Perhaps millions of solar collectors, orbiting like a swarm. Picture surrounding a star 1.4 million kilometers wide, about 100 times wider than Earth, with countless panels capturing its light. The engineering scale is almost beyond imagination. But here's the key question. Would interstellar expansion require at least this level of power? To regularly send ships between stars, to accelerate them to significant fractions of light speed, to shield them from radiation and dust, to build self-replicating probes. The energy demands would be staggering. It seems likely that only civilizations approaching Type 2 could afford that regularly. And Type 3, a civilization using the energy of an entire galaxy, billions of stars, would be capable of projects far beyond our understanding. But here's something interesting. We do not see clear signs of Type 2 or Type 3 civilizations. Astronomers have searched for unusual stars that appear dimmer than expected, as if surrounded by massive energy-collecting structures. They have looked for galaxies glowing strangely in infrared light, which might suggest large-scale engineering. So far, nothing unmistakable has appeared. That silence suggests something. Maybe very few civilizations ever reach Type 2. Maybe harnessing a star's energy is far harder than we think. Or perhaps civilizations choose not to. There are practical concerns. Building megastructures around a star requires materials on a planetary scale. You would need to dismantle entire planets or mine vast asteroid belts. That's not just an engineering task. It's a long-term commitment, lasting centuries or millennia. Would every civilization choose that path? Or would many find more efficient ways to live within planetary limits? There's also the issue of diminishing returns. Perhaps once a civilization becomes highly efficient, it doesn't need massive energy growth. Imagine if your entire society could run comfortably on the energy output of a small power plant. Would you feel the need to build a structure the size of a planet around your star? Maybe not. And then there is risk. Large-scale engineering on a stellar level carries enormous consequences if something goes wrong. If your energy network depends on structures around your star, failures could be catastrophic. So here's a gentle possibility. Maybe most civilizations remain below Type 2. They stabilize at planetary or local system scales. They explore digitally. They improve quality of life. They conserve resources. Without reaching star-level energy use, large-scale interstellar expansion remains rare, and if only Type 2 or higher civilizations can truly spread across the galaxy in a noticeable way, and if those civilizations are extremely rare, then the silence we observe makes more sense. We might simply be in a galaxy where few have crossed that threshold, or perhaps reaching Type 2 requires surviving immense pressures. Political unity, technological mastery, long-term stability. Any small breakdown along the way could halt progress. If becoming a star-powered civilization is extraordinarily difficult, then most life-bearing worlds might never get there. They might remain beautiful, intelligent, thriving, but local, bound to their star. The Kardashev scale reminds us that advancement is not automatic. It's not guaranteed that intelligence leads to unlimited growth. And if very few civilizations ever gain the energy needed for regular interstellar travel, then the number of potential visitors shrinks dramatically. The galaxy might contain life, it might contain intelligence, but perhaps very few reach the scale required to cross the stars in any meaningful way. And without that scale, The vast distances between suns remain what they are: wide, patient, and mostly quiet. So far, we've been thinking about limits, distance, energy, survival. But what if the silence of the galaxy is not only about difficulty? What if it is about caution? There is an idea sometimes called the dark forest. Imagine walking through a dark forest at night. You cannot see far. You don't know who else is out there. You don't know their intentions. You hear a rustle in the bushes. Do you shout out to announce your presence? Or do you stay quiet? In this idea, every civilization in the galaxy is like a hunter in that forest. Each one knows others might exist, but no one knows whether those others are peaceful or hostile. And because distances are so large and communication so slow, there is no easy way to build trust. If you detect a signal from another star, it might have been sent hundreds or thousands of years ago. You cannot quickly ask questions. You cannot clarify misunderstandings. You cannot negotiate in real time. And if another civilization is more advanced than you, it might have technology far beyond your ability to resist. From a purely cautious perspective, broadcasting your location loudly into space could feel risky. Right now, Earth has been sending radio signals for about 100 years. That means our signals have traveled roughly 100 light years in every direction, forming a bubble about 200 light years across. That sounds large, but compared to the Milky Way, which is 100,000 light years wide, that bubble is tiny, like a small ripple in a vast ocean. Still, some scientists debate whether we should actively send powerful messages announcing our presence. The question is simple. If someone out there hears us, what will they do? Of course, this idea assumes hostile civilizations exist, but even if most are peaceful, it only takes one aggressive, expansionist society to make others cautious. On Earth, when new civilizations met historically, the outcome was often uneven. One side had more advanced weapons or technology. The weaker side often suffered. If that pattern holds anywhere in the universe, then staying quiet might be a survival strategy. So here's a quiet possibility. Maybe advanced civilizations do not build bright, obvious megastructures. Maybe they do not broadcast powerful signals. Maybe they deliberately keep a low profile. Energy collection could be optimized to reduce waste heat. Communications might be tightly focused rather than sent in all directions. In other words, they might be deliberately hard to detect. The universe might not be empty. It might just be quiet by design. This changes the question. Instead of asking, why haven't aliens reached Earth? We might ask, why would they reveal themselves at all? If a civilization is comfortable on its home world, or within its own star system, why risk drawing attention? Interstellar travel already carries enormous cost and danger. Adding the risk of hostile encounters might make expansion even less appealing. There's also something else. In a universe where travel takes centuries or millennia, any conflict between civilizations would unfold slowly. You detect another civilization, 1,000 light years away. If you decide they are a threat and send something toward them at 10% of light speed, it would take 10,000 years to arrive. By then, they may have changed completely or disappeared. The slowness of the universe creates uncertainty, and uncertainty encourages caution. It's like hearing a faint sound far away in the dark. You don't know what caused it. You don't know if it is dangerous. You might simply choose to remain still. Some argue that this idea is too pessimistic, that advanced civilizations would outgrow fear, that cooperation might be more rational than aggression. That may be true, but even then, without fast communication, trust is difficult. Imagine sending a message that takes 500 years to arrive. The reply takes another 500 years. A simple exchange of greetings would take a full millennium. Building alliances under those conditions is slow and fragile. So perhaps the galaxy is filled with cautious watchers, each one aware of the possibility of others, each one choosing silence. If that is the case, then the absence of obvious signals does not mean absence of life. It may mean mutual hesitation, and perhaps Earth, still young and noisy, is simply unaware of how quiet the forest really is. We are like a camper, lighting a bright fire and singing loudly, unaware that other campers may be watching silently from the trees. Whether the dark forest is true or not, it adds another layer to the mystery, not just physical barriers, but strategic ones. The universe may not only be vast and slow, it may also be careful. And in a careful galaxy, silence might be the safest choice. There is something quietly puzzling about the galaxy. Even if travel between stars is slow, even if ships move at only a small fraction of light speed, spreading across the Milky Way should not take forever. Let's slow down and picture this. Imagine a civilization that can send ships traveling at just 1% of the speed of light. That's about 3,000 kilometers per second. At that speed, you could travel from Earth to the Moon in about 2 minutes. Compared to light, 1% feels slow, but on cosmic scales it's not. At 1% of light speed, reaching a star 10 light years away would take about 1,000 years. That's a long time by human standards. But once they arrive, they could settle, build, and after a few centuries, send ships onward again. This process could repeat, like ripples in a pond. Now here's the interesting part. Computer models show that even at these relatively slow speeds, a determined civilization could spread across the entire Milky Way in tens of millions of years, maybe 10 million, maybe 50 million. That sounds enormous, but compared to the galaxy's age, over 13 billion years, it's small. If the galaxy's lifetime were a 100-year-old person, 10 million years would be less than a single month. So here's the question that feels heavy and quiet. If even one civilization began expanding 100 million years ago, shouldn't the entire galaxy be filled by now? Shouldn't we see clear signs everywhere? The stars around us are billions of years old. Earth formed about 4.5 billion years ago. There were already stars in the Milky Way long before our sun existed. That means if intelligent life developed around older stars, they could have had a huge head start. Even if intelligent life is rare, it only takes one early civilization to start spreading. So why doesn't the galaxy look obviously colonized? Why don't we see large-scale engineering projects? Why isn't our solar system already claimed? This is sometimes called the expansion timescale problem. It creates tension. On one hand, travel is hard. On the other hand, time is long, very long. And over very long times, even slow processes can achieve large results. Think about plants spreading across land. A single tree drops seeds nearby. Those seeds grow and drop more seeds. Over centuries, a forest expands. No single tree moves quickly. But over time, the forest grows steadily. The galaxy could work the same way. Even if travel between stars takes centuries, once established, each new colony could eventually send out its own missions. Expansion would not require racing ships. It would require patience, and the universe has plenty of that. So why don't we see evidence of this slow wave spreading? One possibility is that expansion is not stable. Maybe early colonies fail. Maybe resources are insufficient. Maybe interest fades. Another possibility is that expansion happens, but not in obvious ways. Perhaps civilizations use their local resources efficiently, without building giant visible structures. Perhaps they alter their own star systems subtly. Or maybe expansion is selective. Instead of filling every star system, they choose only certain types, ones with specific resources or stable conditions. The Milky Way contains hundreds of billions of stars. Many are small red dwarfs. Some are unstable. Some lack suitable planets. If expansion targets only a small fraction of stars, the overall appearance of the galaxy might remain mostly unchanged. There's also a social question. Would a civilization always want to expand endlessly? On Earth, growth has often been linked to survival and competition, but an advanced, stable civilization might not feel pressure to spread. It might prioritize balance over expansion, or it might explore digitally rather than physically. Still, the timescale argument remains strong. Over billions of years, even slow expansion should leave traces, and we do not see obvious traces. No alien cities in our asteroid belt, no giant structures around nearby stars, no probes openly moving through our solar system. The silence becomes harder to ignore. It suggests either that no one started early enough, or that something prevents expansion from continuing indefinitely. Maybe the Great Filter removes most civilizations before they begin spreading. Maybe energy limits keep expansion small. Maybe the dark forest keeps everyone cautious. Or maybe we are simply in a region not yet reached. The Milky Way is huge, 100,000 light-years across. If expansion began far away, the wave might not have reached our neighborhood yet. After all, even at 1% of light speed, crossing the entire galaxy would take about 10 million years, and 10 million years, though short cosmically, is still much longer than human civilization has existed. Perhaps we are living in the quiet before the wave arrives, or perhaps the wave never begins. The expansion timescale problem does not give a clear answer, but it deepens the mystery, because it shows that distance alone may not be enough to explain the silence. Time is abundant in the universe, and when time is abundant, even slow processes can reshape galaxies. Yet the stars around us remain calm, untouched, or at least they appear that way. And that appearance, that vast, ordinary stillness, is part of what makes the question linger so gently in the mind. Where is everyone? There is another possibility we have to consider. Maybe the silence is not about travel. Maybe it is not about fear. Maybe it is not about energy or time. Maybe worlds like Earth are simply rare. When we look at the night sky, it feels full. There are countless stars. Modern telescopes have confirmed that many of them have planets. In fact, planets seem common. On average, there may be at least one planet for every star in our galaxy. That sounds promising. But having a planet is not the same as having a world like Earth. Earth sits at just the right distance from the sun for liquid water to exist on its surface. Not frozen solid, not boiling away. This region is often called the habitable zone. If Earth were just a little closer to the sun, oceans might have evaporated long ago. A little farther, and they might have frozen permanently. To picture this, imagine moving Earth just 5% closer to the sun. That's like shifting your chair slightly closer to a campfire. The warmth increases quickly. Over long time scales, small changes can matter, but distance is only one factor. Earth also has a strong magnetic field. This invisible shield protects us from harmful solar radiation. Without it, our atmosphere could slowly erode away. Mars likely lost much of its atmosphere this way. Today, Mars is cold and dry. Once it may have had rivers and lakes. Earth also has plate tectonics. The slow movement of continents helps recycle carbon through the atmosphere and oceans, stabilizing climate over millions of years. It's like a thermostat that works very slowly but effectively. Without this recycling, carbon dioxide could build up or disappear entirely, pushing the planet toward extreme heat or deep freeze. Then there is our large moon. The moon helps stabilize Earth's tilt. Without it, our planet's axis might wobble more dramatically over time. That could cause extreme climate swings, making long-term stability harder. Some scientists think the presence of a large moon might be important for complex life. Not certain, but possibly helpful. There's also Jupiter. Jupiter is enormous, more than twice as massive as all the other planets combined. Its gravity acts like a cosmic shield, deflecting or capturing many comets and asteroids that might otherwise strike Earth. Imagine living in a house with a large wall blocking debris from a storm. Jupiter plays a role like that. Not perfect protection. Earth has still been hit by asteroids, but perhaps helpful over billions of years. When you add all these factors together, the right distance, stable star, magnetic field, plate tectonics, a large moon, protective gas giants, the picture becomes more specific. Maybe simple life is common. Maybe microbes exist on many worlds. But complex, stable, long-term environments like Earth might be far rarer. The galaxy contains hundreds of billions of stars, but many of those stars are red dwarfs. Red dwarfs are smaller and cooler than our Sun. They can be unstable, producing powerful flares that blast nearby planets with radiation. Planets in their habitable zones must orbit very close to stay warm. That closeness can cause tidal locking. One side of the planet always facing the star, the other in permanent darkness. Could life adapt to that? Possibly, but it adds challenges. Then there are massive stars that burn hot and fast. They may only live for a few 100 million years, too short for complex life to evolve. On Earth, complex animals appeared after billions of years. If a star only shines steadily for a short time, there may not be enough time for intelligence to arise. So here's a quiet question. How many stars are stable for billions of years, have planets in the right zone, with the right chemistry, and long-term climate stability? We are still learning. Telescopes like Kepler and others have found many Earth-sized planets in habitable zones. That is encouraging. But we don't yet know how many of those worlds truly resemble Earth in deeper ways. Water must exist. Atmospheres must persist. Geology must remain active. And stability must last not just for millions of years, but for billions. Earth has been habitable for about 4 billion years. That's an incredibly long stretch of time. If Earth's history were compressed into a single year, complex animals would appear around mid-December. Humans would appear in the final minutes before midnight. So even if a planet is habitable for 1 billion years, that might not be enough for advanced intelligence to evolve. The rarity of Earth-like worlds may not be about location alone. It may be about duration. Long, stable windows of time. If such windows are rare, then intelligent civilizations might also be rare. And if intelligent civilizations are rare, then the nearest one might be thousands or tens of thousands of light years away. At those distances, even light takes ages to travel, and physical travel becomes almost unimaginable. So perhaps the galaxy is not empty. Perhaps it is simply sparsely populated with Earth-like worlds, isolated islands in a vast ocean of stars, beautiful, rare, far apart. If that is true, then the silence above us is not surprising. It is the natural result of rarity. Not because life is impossible, but because the exact combination of conditions needed for long-lasting, complex life might occur only occasionally across the vast stretch of the Milky Way. And in a galaxy 100,000 light-years wide, occasional can still mean very far away. Even if Earth-like planets are not extremely rare, even if simple life appears often, there is another step that may be far more difficult. Intelligence. Not just awareness, not just movement, but tool-using, technology-building intelligence. On Earth, life began very early. The planet formed about 4.5 billion years ago. The earliest signs of life appear more than 3.5 billion years ago. That means life started relatively quickly once conditions allowed it. For billions of years, however, life remained simple. Single-celled organisms ruled the oceans. They were successful. They spread everywhere. They adapted to extreme environments, deep sea vents, frozen ice, acidic lakes, and yet they did not build cities. They did not invent radio. They did not look up at the stars and ask questions. Complex multicellular life appeared much later. around 600 million years ago. That's already nearly 3 billion years after life began. If Earth's history were a 24-hour day, simple life would appear in the early morning. Complex animals would not show up until almost 9 o'clock at night. And even then, intelligence as we know it came much later. Dinosaurs lived for about 165 million years. That's a stretch of time so long that if you laid it out like a road at 1 meter per 1,000 years, it would stretch 165 kilometers, longer than many cities. Yet during that vast span, no species developed radio telescopes. Large brains are expensive. They require energy. They require stable environments. They require long childhoods for learning. Humans spend many years growing and learning before becoming independent. That long developmental period is unusual in the animal kingdom. So here's a quiet question. Is intelligence inevitable? Or was it a rare accident? On Earth, intelligence in the human sense appears only once. There are intelligent animals: dolphins, elephants, crows, octopuses. They show problem-solving skills and social awareness, but none developed advanced technology. Why? One possibility is physical limitation. Dolphins are smart, but they live in water. They do not have hands to manipulate tools easily. Fire is difficult underwater. Elephants are strong and social, but their body shape may not lend itself to fine manipulation the way human hands do. Crows are clever, but small size and limited lifespan may restrict long-term technological growth. Humans have a unique combination: large brains, dexterous hands, upright posture freeing the hands, social cooperation, language complex enough to share abstract ideas. That combination may not be common. Imagine evolution as a branching tree with millions of possible paths. Intelligence like ours might require passing through a narrow gap, a specific sequence of traits aligning over time. If any one step fails, the path diverges. Perhaps many planets host rich ecosystems filled with plants and animals, but the exact path toward tool-building intelligence might be rare. There's also the matter of stability. On Earth, mass extinctions have occurred several times. One asteroid impact 66 million years ago ended the age of dinosaurs. If that asteroid had missed, perhaps dinosaurs would still dominate. Would mammals have risen? Would humans have evolved? Small events can shift evolutionary direction dramatically. If intelligence depends on a series of unlikely events aligning, then it may not happen often. And even if intelligence arises, it must persist. Early humans faced harsh environments: ice ages, predators, limited resources. If early Homo sapiens had gone extinct, another intelligent species might not have emerged. The window for intelligence may be narrow. Stars like our Sun have finite lifespans. Our Sun will remain stable for about 10 billion years in total. It is roughly halfway through. If complex life takes billions of years to appear, and intelligence appears near the end of that window, then the opportunity for advanced civilizations may be limited. On some planets, conditions may change before intelligence has time to develop. On others, catastrophic events may reset evolution repeatedly. So perhaps simple life is common. Perhaps complex ecosystems are common, but intelligent, tool-building species might be rare. And if intelligence itself is rare, then technological civilizations are rarer still. Imagine the Milky Way with 100 billion stars. Even if 1 in a million stars hosts intelligent life, that would still be 100,000 civilizations across the galaxy. That sounds like a lot. But spread across 100,000 light years, that averages roughly 1 civilization per 1,000 light years in each direction. That's far. At those distances, even radio signals take 1,000 years to travel. Physical travel becomes nearly impossible on short timescales. And if the number is even lower, 1 in 10 million, then the nearest neighbor might be several thousand light years away. In that case, the silence becomes understandable. We might simply be very far apart. The intelligence bottleneck suggests that the leap from life to advanced technology may be one of the rarest steps of all. Not impossible, not unique to Earth necessarily, but uncommon enough that neighbors are separated by vast stretches of space. If so, then the reason aliens haven't reached Earth may not lie in hostility or collapse. It may lie in rarity. Intelligence might be a delicate outcome of billions of years of chance, environment, and survival. And delicate outcomes do not appear everywhere. They appear occasionally, quietly, far apart, across a galaxy that is large enough to keep those rare sparks separated by thousands of light years of calm darkness. There is another possibility that feels closer to home. Maybe intelligent civilizations do appear. Maybe they develop technology. Maybe they even begin to explore their own star systems. And then something goes wrong, not because space stops them, but because they stop themselves. When a species becomes technologically advanced, it gains power. Power over energy, power over biology, power over its own planet. On Earth, in just the last 100 years, humans have learned to split the atom. A single nuclear weapon can destroy a city in seconds. Thousands of them exist. We have altered the chemistry of our atmosphere. We have built machines that can modify genes. We are developing artificial intelligence systems that can learn and act in complex ways. All of this happened in about a century. That's incredibly fast. If Earth's entire history were 100-year human life, modern technology would appear in the last few hours before midnight. So here's a quiet question. Can wisdom keep up with power? Technological growth can move quickly, but cultural, political, and ethical systems often change more slowly. It's like giving a teenager the controls of a powerful airplane without enough training. The machine can do incredible things, but small mistakes can have huge consequences. One possibility is nuclear war. During the Cold War, humanity came close to nuclear conflict several times. A few misunderstandings, a few technical errors, and the outcome could have been catastrophic. Even a limited nuclear exchange could cause global climate effects, crop failures, and widespread disruption. A full-scale conflict might threaten civilization itself. Another possibility is environmental collapse. Industrial activity has already changed Earth's climate measurably. Rising temperatures, melting ice, shifting weather patterns. Our planet is about 12,700 kilometers wide, roughly the distance of a long road trip across a continent. And yet, human activity has altered systems that operate across the entire globe. If environmental systems become unstable, societies may face food shortages, migration pressures, and conflict. It does not require dramatic extinction. It only requires prolonged instability to limit technological progress. Then there is biotechnology. The ability to edit genes holds enormous promise. It can cure diseases, it can improve crops, but it also carries risk. Engineered pathogens, accidental releases, or misuse could have global consequences. And artificial intelligence presents another layer. Advanced AI systems can analyze data, make decisions, and operate autonomously. In the future, they may manage infrastructure, defense systems, and critical networks. If such systems malfunction, are misused, or act in ways not fully understood, the consequences could be significant. This does not require malevolence, it only requires complexity. As systems become more interconnected, failures can cascade. Think of a large power grid. If one part fails, it can trigger failures elsewhere. The more tightly linked the system, the more carefully it must be managed. Now imagine a planetary civilization relying on complex networks for energy, food distribution, communication, and security. A small disruption could ripple outward. So here's a gentle thought. Perhaps many civilizations reach a stage like ours. They discover powerful technologies, they expand their capabilities rapidly, and then they face a narrow window of vulnerability, a period where their power is great, but their stability is fragile. If they navigate that window successfully, they may become long-lasting and stable. If they fail, their technological phase may be brief. Maybe the galaxy has seen many such stories, planets where intelligent beings looked up at their stars, built machines, sent early probes into orbit, and then, within a few centuries, something shifted. Conflict, collapse, unintended consequences. The planet remains. Life continues in some form, but the technological spark fades. It's like lighting a match in a dark room. It flares brightly for a moment, then goes out. If most civilizations extinguish themselves within a few hundred or thousand years of becoming advanced, then the overlap between different civilizations becomes very small. Two species would need to exist at the same time and survive long enough to reach each other. Given the vast distances between stars, that overlap may rarely occur, and so the silence of the galaxy might not be due to impossibility. It might be due to fragility. Advanced technology brings enormous opportunity. It also brings enormous responsibility. The universe does not seem to protect civilizations from their own choices. If self-destruction is common, then reaching interstellar travel becomes rare not because of physics alone, but because of sociology, because managing power over long periods is difficult. This idea feels personal. It suggests that the question, why haven't aliens reached Earth, is connected to another question. Will we reach the stars, or will our own challenges limit us before we get there? The answer is not written yet, but the possibility remains that many worlds ignite with intelligence and only a few burn long enough to cross the vast, patient spaces between the stars. Let's imagine something hopeful. Let's imagine that intelligent civilizations are not rare. Let's imagine that many survive their dangerous early years. Let's imagine that they are peaceful, curious, and patient. Even then, there is another quiet barrier: communication itself. Light travels incredibly fast, about 300,000 kilometers per second, fast enough to circle Earth 7 times in 1 second. And yet, across space, even light feels slow. If a civilization is 100 light years away, any message they send takes 100 years to reach us. If we reply immediately, our response takes another 100 years to reach them. That means a simple hello and hello back exchange takes 200 years, 2 centuries for one round of conversation. If they ask a question and we answer, another 200 years pass. A short dialogue could stretch over 1,000 years. It's like writing a letter that your great-great-grandchildren will receive, and hoping their great-great-grandchildren will write back. Would societies maintain focus over such timescales? Even stable civilizations change. Languages shift. Political systems evolve. Values transform. If a signal leaves a planet in the year 1500, the world receiving it in 2500 may be very different from the one that sent it. And if the civilization that sent the message collapses before receiving a reply, the exchange ends. Now imagine distances of 1,000 light years. That's not extreme in galactic terms. The Milky Way is 100,000 light years across. At 1,000 light years, one exchange takes 2,000 years. If you began a conversation today, the answer would not return until the year 4026. That's longer than all of recorded human history. Here's a gentle question. Would a civilization invest effort into communication that spans millennia? Perhaps, but it requires patience beyond our current cultural habits. There is another complication. Signals weaken over distance. Radio waves spread outward, like ripples in a pond. The farther they travel, the more they spread out and fade. By the time our early radio broadcasts have traveled 100 light years, they are extremely faint, like trying to hear a whisper across an entire continent. To detect them clearly, another civilization would need enormous, sensitive receivers, and they would need to be listening in the right direction at the right time. Space is vast. Stars move. Civilizations may not continuously broadcast strong signals. And here's something else. We have only been listening seriously for alien signals for about 60 years. 60 years. If the universe were a 24-hour day, that would be less than 1,000th of a second. It's possible that signals passed Earth thousands of years ago, before we had technology to detect them. Or signals may pass thousands of years from now. We are sampling a very small slice of time. Imagine standing by a highway for 1 minute and concluding that no cars exist because none passed during that minute. The highway might be busy at other times. Communication also depends on technology compatibility. We use radio waves because they are convenient for us. Another civilization might use methods we haven't imagined. Laser pulses, neutrinos, quantum communication. If we are not looking in the right way, we might miss signals entirely. There is also the issue of synchronization. For communication to occur, both civilizations must be technologically capable at the same time. If one civilization sends signals 5,000 years ago, and another only develops radio 3,000 years later, the window does not overlap. It's like two people trying to call each other, but never having working phones at the same time. So perhaps intelligent civilizations are out there. Perhaps some have sent signals. Perhaps some are listening. But the combination of distance, delay, fading signals, timing, and technological mismatch makes successful communication rare. And without communication, awareness remains limited. Even if a civilization 2,000 light years away exists right now, we would not know unless their signals reach us. And even if we detect them, meaningful exchange would unfold over thousands of years. It becomes less like a conversation and more like archaeology. We might detect a signal that tells us what they were like long ago, not what they are like now. By the time we respond, they may have changed beyond recognition. The communication delay problem doesn't mean we are alone. It means we may be out of sync, separated not only by distance, but by time gaps that stretch across centuries and millennia. In such a universe, silence does not necessarily mean emptiness. It may simply mean that the voices are too far apart, too faint, or speaking at times that do not overlap. And so the night sky remains quiet, not because no one is speaking, but because the timing and distance make hearing each other extraordinarily difficult. When we look up at the night sky, the stars seem evenly scattered, but the Milky Way is not uniform. It has structure. Spiral arms filled with gas and dust, dense regions near the center, quieter neighborhoods farther out. And where we live in the galaxy may matter more than we realize. Our sun sits about 26,000 light years from the center of the Milky Way. If the galaxy were the size of a large city 100 kilometers across, we would be living in a calm suburb about halfway between downtown and the outer edge. The center of the galaxy is busy. Stars are packed much closer together there. Instead of being separated by several light years, some stars are only a fraction of a light year apart. That's like houses built almost wall to wall compared to the wide spacing in rural areas. With stars closer together, travel between them becomes easier. Shorter distances mean shorter journeys. If civilizations form more often in those dense regions, they might cluster near the galactic center. Meanwhile, our region, in one of the quieter spiral arms, may be relatively isolated. The space between neighboring stars near us averages about 4 to 5 light years. That's already a challenge, but near the center, that spacing can shrink significantly. Shorter gaps reduce travel time and energy requirements. So here's a gentle possibility. Maybe intelligent life exists in clusters. Civilizations forming in dense star regions might interact with each other more frequently. They might expand locally, but vast stretches of the galaxy, including our neighborhood, might remain sparsely populated. The Milky Way is about 100,000 light-years across. Even if advanced civilizations exist in one region, that does not guarantee they have reached all regions. Think about Earth's oceans. If humans only lived on one continent, large parts of the planet would remain empty. Even if they slowly expanded, remote islands might stay untouched for long periods. And there's another factor. The galactic center is not only dense, it is also energetic. There is a supermassive black hole there. It does not actively consume nearby stars constantly, but the region experiences higher radiation levels and more frequent stellar events. Supernovae, exploding stars, are more common in dense regions. These explosions release powerful radiation that can affect nearby planets. So dense regions may be better for travel, but harsher for stable life. Meanwhile, outer regions like ours are quieter and safer, but more spread out. It's a trade-off. Perhaps most advanced civilizations arise in specific sweet spots, regions that are not too chaotic, but not too isolated either. The galaxy may have habitable bands, similar to how planets have habitable zones around stars, and maybe Earth lies near the edge of one such band. There's also vertical structure. The Milky Way's disk is only about 1,000 light-years thick in most places, compared to its 100,000 light-year width. That's like a thin pancake. Our Sun orbits within this disk, occasionally moving slightly above or below the central plane over millions of years. These movements can change exposure to radiation and passing stars. Galactic geography shapes long-term conditions for life. So here's a quiet thought. Even if intelligent civilizations are scattered throughout the Milky Way, they may not be evenly distributed. They might cluster in regions with favorable star density and stability. And if we are located in a relatively calm and somewhat isolated area, our nearest advanced neighbor might be thousands or tens of thousands of light-years away. At those distances, travel and communication become extremely difficult. Even light takes tens of thousands of years to cross from one side of the galaxy to the other. So our position matters. We may not be in the center of activity. We may not be in a busy galactic hub. We may be in a quieter suburb, and quiet suburbs can feel empty, even if cities exist elsewhere. There's something comforting about that image. The galaxy might not be silent everywhere. It might simply be that we are far from the noise, far from the clusters, far from the crossroads of interstellar travel. If civilizations expand primarily within dense regions, where stars are close together, they might form networks there. Meanwhile, outer spiral arms could remain largely untouched. The Milky Way is vast enough to allow that. It's large enough for some areas to be lively, and others to remain quiet for millions of years. So perhaps the reason aliens haven't reached Earth is partly geographical. Not because they do not exist, but because we are located far from where expansion or interaction is easiest. In a galaxy 100,000 light-years wide, position matters, and our position may simply be remote, like a house at the edge of a forest, far from the main paths, peaceful, calm, and mostly undisturbed. So far, we have stayed within our galaxy. The Milky Way is already almost too large to fully imagine. 100,000 light-years across, holding hundreds of billions of stars. But beyond it, there are billions of other galaxies. And here is something both fascinating and quiet. Most of them are already unreachable, not because of fuel, not because of danger, but because of the way the universe itself behaves. The universe is expanding. This expansion was discovered nearly a century ago. When astronomers observed distant galaxies, they noticed something surprising. Almost all of them are moving away from us. The farther away a galaxy is, the faster it appears to recede. It's not that galaxies are flying through space like rockets. It's that space itself is stretching. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other. not because they are crawling across the surface, but because the surface itself is expanding. Our universe works in a similar way, and here's where it becomes even more interesting. The expansion is not slowing down, it is accelerating. Something called dark energy appears to be pushing space apart faster over time. We don't fully understand dark energy, but we can measure its effects. Right now, galaxies that are very far away are moving away from us faster than the speed of light due to this expansion. That might sound impossible. Earlier we said nothing can move faster than light, and that's true for objects moving through space. But space itself can expand without that limit. So here's a quiet consequence. There is a cosmic horizon. Beyond a certain distance, galaxies are receding from us so quickly that light emitted today will never reach us, no matter how long we wait. Even if we lived for trillions of years, their light will never arrive. It's like watching boats drifting away on an ever-expanding ocean. Some drift slowly enough that you could still reach them with a fast ship. Others drift away so quickly that even your fastest vessel could never catch up. This means that much of the observable universe is already permanently out of reach, not just physically unreachable. Even communication is impossible beyond a certain point. If a civilization exists in a galaxy billions of light years away, and that galaxy is receding fast enough, we will never exchange signals. The gap will only grow. Even within our own local group of galaxies, a small cluster that includes Andromeda, gravitational attraction holds us together. We can, in theory, travel within this group if we had enough time and technology. But beyond that local group, expansion dominates. Over tens of billions of years, distant galaxies will fade beyond view entirely. Future astronomers, living far in the future, may see only our merged local group and nothing else. The rest of the universe will have slipped beyond their horizon. So here's a gentle reflection. Even if intelligent civilizations are common across the universe, most of them are forever isolated from us by cosmic expansion. The observable universe is about 93 billion light-years across. That's its diameter. If you imagine it as a sphere and shrink it down to the size of Earth, about 12,700 kilometers across, then our entire Milky Way would be smaller than a grain of dust on that sphere. And beyond that dust-like galaxy lie countless others, yet most are already drifting beyond permanent reach. This means intergalactic travel is even more difficult than interstellar travel. Crossing between galaxies would require millions of years at high speed, and for many galaxies, it is not just difficult, it is fundamentally impossible, because space is expanding too fast between us. So, when we ask, why haven't aliens reached Earth? We often picture civilizations traveling across the universe, but in reality, the universe is not a stable stage. It is stretching, pulling galaxies apart, gradually isolating them. If advanced civilizations arise in distant galaxies, they may never know we exist, and we may never know they exist, not because of failure, not because of silence by choice, but because the fabric of space separates us permanently. It's like living on islands in an ocean that is growing wider every second. Even if ships exist, even if explorers are brave, the ocean itself keeps expanding. So perhaps the silence is not only about the Milky Way, perhaps it is about the structure of the universe itself. A universe that began connected, but is slowly fragmenting into isolated regions. In that sense, distance may not just be large, it may be final. And that realization adds a calm but profound layer to the question. The stars are far, the galaxies are farther, and beyond a certain horizon, they are forever beyond our reach. There is one more possibility that feels both surprising and strangely hopeful. What if the silence is not because civilizations failed, not because they destroyed themselves, not because space is impossible to cross, but because we are early, very early? The universe is about 13.8 billion years old. That sounds ancient. And it is, but stars come in many types, and not all of them live for the same amount of time. Our Sun is a medium-sized star. It will shine steadily for about 10 billion years in total. It is roughly halfway through its stable life. But most stars in the universe are much smaller than the Sun. They are called red dwarfs. Red dwarfs burn their fuel very slowly. Some of them can live for trillions of years. Trillions. That is not a small difference. If the age of the universe so far, 13.8 billion years, were a single day, a trillion years would be more than 2 months on that same scale. In other words, the universe is still young compared to how long it could last. Most red dwarf stars have barely begun their long, steady lives. And here's the interesting part. Planets around red dwarfs could remain stable for trillions of years. That's thousands of times longer than Earth has existed. So here's a quiet question. If intelligent life takes billions of years to develop, and most stars will last for trillions, when would you expect most intelligent civilizations to appear? Early in the universe? Or much later? It's possible that we are among the first wave. Our Sun formed about 4.6 billion years ago. Earth cooled quickly, and life appeared relatively early. But complex life took billions of years to emerge. If planets around red dwarfs remain habitable for trillions of years, they have far more time for evolution to experiment, far more time for intelligence to develop. Imagine a planet that remains stable not for 4 billion years, but for 1 trillion years. That's like giving evolution 200 times longer than Earth has had so far. With that kind of time, the chances for intelligence might increase. So perhaps the galaxy is quiet right now, because most stars are still in the early chapters of their long lifespans. We may be living near the beginning of the cosmic story. It's like arriving at a theater before the play has truly begun. The seats are empty, not because no one will come, but because the show starts much later. There is another factor. The early universe was more violent. In its first few billion years, star formation was intense. Supernovae were more common. Radiation levels were higher. Heavy elements, the carbon, oxygen, and iron needed for rocky planets and life, were less abundant at the very beginning. These elements are forged inside stars and spread through supernova explosions. Over time, the universe became richer in these building blocks, so perhaps conditions for Earth-like planets became more favorable only later in cosmic history. Our planet may have formed during a sweet spot, not too early, not too late. But red dwarf systems may become ideal habitats over extremely long timescales. If most intelligent life arises around long-lived stars, and if those stars have barely begun their stable phase, then the majority of civilizations may lie in the far future, trillions of years from now. We are only 13.8 billion years into what could be a universe lasting for 100 trillion years or more. That means we are in roughly the first 1% of the universe's potential lifetime. If you compare the universe's lifespan to a 100-year human life, we are living in the first year. So perhaps the silence above us is not a sign of emptiness. It may be the calm before a much busier era. Future galaxies may be filled with intelligent beings. Future skies may hold countless technological civilizations. But right now, the stage may still be mostly quiet. This idea changes the emotional tone of the question. Instead of asking, "Where is everyone?" with frustration, we might ask, "Has everyone simply not arrived yet?" Maybe we are early explorers in a young universe. Maybe we are among the first to look up and wonder. That possibility carries responsibility. If we are early, then what we choose to do matters. We may become part of that future wave, or we may remain a brief spark in an otherwise quiet, early cosmos. The stars above us may one day be joined by countless others, thinking similar thoughts. But for now, the universe may simply be in its opening chapters, and we are here, near the beginning, listening, wondering, in a cosmos that has barely started its long story. After walking through distance, through energy, through time, through survival, rarity, caution, and cosmic expansion, we arrive at a quiet possibility. Aliens may exist. They may be intelligent. They may be advanced. They may have cities, art, science, and curiosity just like we do. And yet, the universe itself may simply be too vast, too slow, too demanding, too unforgiving. Distance is not just a number on a page. The Milky Way stretches 100,000 light-years across. If you could somehow drive across it at highway speed, about 100 kilometers per hour, the journey would take longer than the age of the universe. Even light, the fastest thing we know, needs 100,000 years to cross from one side to the other. That means if a civilization on the opposite side sent a signal when humans were first learning to farm, we still would not have received it yet. Energy is not just about building a bigger engine. Accelerating even a modest spacecraft to a fraction of light speed requires energy comparable to what entire planets produce over years. Shielding against radiation and dust adds mass. Mass demands more fuel. More fuel adds complexity. Time does not cooperate. Even if travelers experience only decades on board due to time dilation, centuries or millennia pass elsewhere. Civilizations drift out of sync. Communication crawls at light speed. A simple exchange can take hundreds or thousands of years. Geography matters. We may live in a quieter suburb of the galaxy, far from denser clusters where interaction is easier. The universe itself expands. Galaxies slip beyond permanent reach. And perhaps most profoundly, intelligence and stability may be rare or brief. Life may appear often, but advanced civilizations might flicker like candles, bright for a moment, then gone. Or perhaps we are simply early, living in a young universe whose longest-lived stars have barely begun their steady glow. When you place all of these pieces together, something changes. The silence stops feeling mysterious. It starts feeling natural. Imagine standing on a vast beach at night. The ocean stretches beyond sight. You know there are other islands somewhere far away, but the water between you is thousands of kilometers wide. You have no ship capable of crossing it easily, and even if someone on another island lights a fire, the curve of the earth hides it from view. The darkness does not mean the islands are empty. It means the distances are enormous. Perhaps the most unsettling possibility is not that aliens are hiding. It is that distance itself is the answer. Not hostility, not conspiracy, not cosmic isolation by choice, just scale. The universe is about 93 billion light-years across in observable diameter. If you shrank it down so that the entire observable universe were the size of Earth, our entire galaxy would be smaller than a speck of dust. And within that speck of dust, we orbit a very ordinary star. We often imagine space as crowded, but when you stretch it to true scale, it becomes sparse beyond intuition. Stars are separated by trillions of kilometers, galaxies by millions of light-years. It may not take much rarity to create silence in such an environment. Even if intelligent life appears thousands of times across the galaxy, those civilizations could still be separated by thousands of light-years, too far for easy travel. Too far for quick conversation, too far for regular contact, and so each world may look up at its own sky, wondering, listening, hoping, perhaps somewhere at this very moment, another species is asking the same question. Where is everyone? They may be running through the same possibilities: distance, energy, time, fragility. They may feel alone too. Not because they are unique, but because the universe is wide and patient. There is something strangely comforting in that thought. The silence may not be a rejection, it may simply be a reflection of the vastness we inhabit. We are young, we have been capable of detecting signals for less than a century, less than a heartbeat in cosmic terms. Perhaps one day we will build better instruments. Perhaps we will spread slowly into our own solar system. Then beyond, perhaps millions of years from now, humans, or whatever we become, will stand on another world, looking back at Earth as a distant star. Or perhaps we will remain here, caring for this one planet, content in our corner of the galaxy. The question of why aliens have not reached Earth does not end with a single answer. It unfolds into many possibilities, each one grounded not in fantasy, but in the simple, steady rules of physics and time. The universe is not hostile in an obvious way. It is just very, very large. And in something that large, even neighbors can remain forever unseen. So the night sky stays quiet, not empty, just vast. And we remain here, small but aware, asking questions beneath a canopy of stars that stretch farther than the mind can comfortably hold. Perhaps that quiet is not something to fear. Perhaps it is simply the natural sound of distance.